So where we ended up there was a weird place. And what we were saying was that if you're at the surface of the Earth, for example, and you want to throw a ball up, so that it never comes down, right? We make a couple definitions. The first definition is, well, we know that in a planetary body, near a planetary body, kinetic energy is the same, but the gravitational potential energy is this weird thing. So where r is the center-to-center distance, we've seen that before, okay? G is the universal gravitational constant, m1 is the mass of the planet or whatever body you're near, and then mass 2 is the mass of your object, right? We've seen this before. And what we're saying is, if I want to throw this so that it never comes back, that means that the total energy, total mechanical energy is going to be equal to 0, because we're saying that at infinity, all right, r is going to be equal to infinity, v is going to be equal to 0. Therefore, ug is equal to 0 and k is equal to 0. The three triangle dots means therefore. I don't know if you guys got that memo, therefore. And then so if I want to say that that equals 0 and that is equal to u plus k, so 0 is equal to negative g m1 m2 divided by r plus 1/2 mv squared. Add this term to both sides, we end up with g m1 m2 divided by r is equal to 1/2 m v squared. Now, which m is this? You can just talk out loud.
Cool.
So m of the ball, right? So that's m2 in this case. So, looking at this, I end up with g m1 divided by r is equal to 1/2 v squared. So, v, the escape speed, is equal to the square root of 2gm all over r. Now, this r is the distance from the center, right? The r is the distance from the center. So, in the context of you say like, well, what is the escape speed at the surface of a planet? It'll be the radius of a planet. But you can still ask the question, well, what is the escape speed out here at one radius, right? Anyway, that's that. Is that cool? Now, then we always get these questions, right? We always get these questions to say, look, there's a new planet, okay? New planet, where the mass of the new planet is equal to half the mass of the Earth. And the radius of the new planet is also equal to half the radius of the Earth. How does the escape speed at the new planet compared to the escape speed at the Earth? And we'll do ratio. Okay? So there's a question like this. Is that cool? So this type of question is the kind we see where they're not actually asking you to solve. They're not asking you what the escape speed is. They're saying, like, how does it compare? And I actually like this question. It makes it a little bit easier to do. Oh, no, not this one. Nick and Steven and Bojan. Thomas. So, let's do this in 2 steps. If I want to find the escape speed at the Earth, okay? So, V escape for the Earth. It's going to be equal to the square root of 2g mass of the Earth divided by the radius of the Earth. Is that cool? You guys see this phrasing here? Is that okay for you? All right. I will say that escape speed is a concept they're going to want you to know and know the equation for, but isn't going to be on the equation sheet. So you're going to have to understand where it comes from, like this construct that I went through right here. So how am I going to write the escape speed for the new planet? So it's going to be equal to the square root of 2g mass of the new planet, m new, divided by the radius of the new planet. Now, here's what's interesting about this. What I can do here is I can just substitute in what I know. The mass of the new planet is half, right? So I'm going to say it's 0.5 mass of the Earth. You see the substitution I did? It's just a really standard substitution. Divided by 0.5 radius of the Earth. Is that cool? All right, and what happens inside here then? Those 0.5s magically disappear. So this is the escape speed at the new planet. And what do I notice? Is it the same? You see how those two phrases, those two expressions for the equation are the same thing? So plugging in here and seeing how this one compares to this one is the way you want to do it. Then the real question is this. How does the acceleration due to gravity on the new planet compare to the acceleration due to gravity on the Earth? So this is the type of question that we see often. Where they'll say, oh, you got a new planet where you got a new mass and a new radius. How does the escape speed compare? And then how does the gravitational acceleration compare? So in order to do that, we have to have a construct for the free fall acceleration. Well, we know that for an object near the surface, the gravitational force is equal to the gravitational force. And then we can just plug and chug it. We got little mg, mass of the ball times gravitational acceleration is equal to g, mass of the planet, times the mass of the ball, all divided by the radius squared. So g is equal to big G, mass of the planet, divided by the radius of the planet squared. So if I want to do it for Earth, I'm going to say g for Earth is equal to g, mass of the Earth, divided by the radius of the Earth squared. Yeah?
Does that g in the force equation have to be negative?
No. That's a great question. So what we're going to do is we're going to use the directionality of both forces. So this one is in the down direction, and this one is also in the down direction. So since they're both in the down direction, we just keep them both positive. All right, so let's do it over here. What's the g for the new planet? Well, it's going to be equal to g, mass of the new planet, divided by the radius of the new planet squared. Let's make our substitution. What do we know about the mass of the new planet compared to the mass of the Earth? It's half. And then what about the radius? Also half. But what do we notice about the radius term? It's squared. You see that? That's going to be the difference maker here, is the fact that sometimes it's squared, and we're going to pay attention to that. So that means that g for the new planet is going to be equal to, ooh, I don't know what happened there. Got a little distracted. G. Now I'm going to have 0.5 on top. Here, I'll write it this way. I have 0.5 on top. I have g mass of the Earth. And then on the bottom, I have 0.5 squared times radius of the Earth squared. And you have 0.5 on top and 0.5 squared on the bottom, which is going to be 1 divided by 0.5. But if you divide by 0.5, what's that the same thing as like multiplying by 2? So what we're noticing here is that if I now compare these two, the g of the new planet is 2 g mass Earth divided by radius Earth squared. And so it's twice as much. So this would be a 2-to-1 ratio. So I find that really interesting that you take the planet and if you shrink it down to half the mass and half the radius, the escape speed is the same, but the acceleration due to gravity is twice as much. Now, here's the deal. If I compare these two things, okay? If I compare these two things, let's see what they look like compared to one another. Escape speed is equal to the square root of, oh my God, what is that? Is that cool? And my g value is equal to g over r squared. Can I write escape speed in terms of the g value? Try that now. I want you to write this where it says v escape is equal to and then something times g. All right, see if you can do that now. It would be cool if those two things were somehow related. And I got this new card trick I've been working on. It is a killer. Wait till you guys see. Yeah?
Is there supposed to be a 2 in the numerator of the
Oh,
escape?
absolutely. Yeah, thank you so much. I totally forgot. Thank you so much. I don't think this is as easy as it seems like it should be. All my life growing up, I never had seasonal allergies. Then all of a sudden, in like the last 5 years, like spring hits, and I'm just like, 50 years old, almost. Man, can you get almost 50? Dude, I'm old. When did that happen? You know what happened? I started having children. The last 10 years went by and like a heartbeat. All of a sudden I'm old. You guys want to see? So this is actually a cool thing. Look at the term, GM over R, correct? You see that term in there? It looks like this one, doesn't it? How can I make this thing look like GM over R? What would I have to do to this side to get it to be GM over R? I would multiply by R. If I take this side and I multiply by R, what am I going to get? Am I going to get GM over R? You see me on that? Yes or no? Okay? But if I'm going to multiply this side by R, what do I have to do to this side? You got to multiply by R, right? That's like the algebra rule. So I have GM over R. I'm going to substitute that thing in right there. So I'm going to say that my escape speed then is equal to the square root of 2 is GM over R, but that's just GR. Look how sneaky that is. How sneaky is that? Very sneaky. Very, very, very sneaky. All right, so let's talk about our planet. How do we figure out how big the acceleration due to gravity is? Well, it depends on two things, right? So when I look at my G value, it's GM over R squared, right? So if I want to make my G value bigger, what are two things I can do? I want to make my acceleration to gravity at the surface bigger. What are the two things I can do? I can increase the mass, or I can decrease the radius. True? Now, it turns out that decreasing the radius is significantly more effective in that because it's got a square term in here, right? But we saw that the escape speed actually depends on the acceleration due to gravity. So a bigger acceleration due to gravity would give you a bigger escape speed, right? You'd have to be going faster. This all makes perfect sense in your head because if you're here with your ball and you throw it up, it's going to go up and come back down. True? Is that all right? Now, let's say I want to throw it so it goes higher. No big whoop. What do I have to do? I'm going to throw it hard. I have to give it more speed. Yes? So I'm going to give it more speed. It's going to go up and come back down. But then what I'm going to do is I'm going to increase the mass even a little bit more. Does that sound good? Another thing I can do is like, forget that. How am I going to get my ball to go faster? Well, you know that you have to apply a force on the ball, true? So the acceleration of your ball is the force you throw it with over the mass of the ball. Or we could do it this way, that the force times the time is equal to the mass times the change in velocity, right? If I want my ball to have a bigger change in velocity, I'm going to have to throw it harder, true? Or, if I'm throwing as hard as I can, if I want my speed to be bigger, I need my mass to be smaller, right? Because if you're going to throw it as hard as you can, if it's a smaller something, it's going to go faster, true? So what I'm going to do is, I'm going to say, screw you, mass. I'm going to make my ball lighter, and guess what? Now my ball goes back, it goes higher. But then what we do is we increase the mass some more, and we're back to here. So I'm like, forget this. I'm going to take my ball, and I'm going to make it the lightest thing ever. And what I'm going to do is I'm going to make it a flashlight. So I'm going to shine my flashlight here. And so my beam of light just goes out as far as it can go. I'm like, what's up now? But then what do they do? Is they're like, that's fine. I'm going to take my mass, I'm going to make it bigger, I'm going to take my radius, I'm going to make it smaller, so that my G value is so big that not even light can make it off the planet. And if your thing is so massive with such a small radius that not even light can get off of it, that's a black hole. Because if it's up in the night sky and there's no light getting off of it because the gravitational acceleration is so big, then I'm going to point my telescope at it, but there's no light coming off of it. So what's it going to look like in the sky? It's just going to look like a black hole in the sky. That's what it is. So it's a star, not a planet, but a star, that is so massive in such a small radius that the G value is such that the G value is such that the escape speed is bigger than the speed of light. Come on, tell me that's not cool. Right? I mean, if your escape speed is bigger than the speed of light, no light can escape from you.
What's the speed of light?
We use the little letter c for speed of light. It's 3 times 10 to the 8 meters per second. It's about 187,000 miles per second. Now, light isn't infinitely fast. It has a certain speed, okay? But it's real fast. Like, take your finger and put it in the air like this, okay? And I want you to make one circle, okay? Now make 2 circles. Now make 6 circles, okay? How long do you think it took you to make 6 circles? Probably about a 1 Mississippi. Light is so fast that if I turned on my flashlight and it bent around the Earth, the light beam would go around the Earth 6 times in 1 second. I mean, the Earth is real big. It's 24,000 miles around the Earth. And it can do that 6 times, about 6 times in 1 second. But, go ahead, there's 2 questions. Go ahead. Go ahead,
Well, I
Anthony.
was gonna ask, do we know of anything faster than light that we can measure?
No, so if you're talking about a particle, we're trying to get something to move faster. There's a real problem, and I'll tell you what the problem is in a second. Let me answer this question.
I just forgot to put my finger down.
He was like this, and I'm like, he has a question. He did not have a question. That's funny. So the speed of light not being infinitely fast is a real issue. Okay, I'm talking like a real issue, because I'm going to throw this. I'm going to throw this apple up so it goes down and goes back, goes up and comes back. Ready? Okay. Did you all see the apple go up and come down? Right? Did you all experience it happening at the same time? The answer is no. The answer is absolutely not. She experienced it before anybody else, because when I caught this, she saw the light hit here, and get into her eyeballs. But in a very specific way, the light had to go all the way back there to Anthony. It had a farther distance to travel. Therefore, he actually saw it happen later. They did not actually experience it at the same time. Now, in here, we don't notice a difference, and we don't care. But if he was very far away, that might be a problem. Or if he was moving away from us at, let's say, half the speed of light, the light would take a very long time to get to him. True? So we couldn't agree on when this thing happened. How do you not agree? Yeah?
When you say like very far away before you would notice it, how far is that?
That's a great question. So the moon is about 1 light second away, which means it takes a full second. It's a little more than that, but we'll just estimate it. A full second for the light to reach, from the moon to reach us. Okay? The sun is 8 light minutes away. So when I'm looking at the sun, I don't see what the sun looks like right now. I see what it was looking like literally 8 minutes ago. If the sun were to somehow blink away, we wouldn't know for 8 full minutes. This becomes a real problem because the nearest star to ours is 2.4 light years away. So when I look at, we can't see it from the northern hemisphere, but let's just pretend. Alpha Centauri is the closest star to ours, and when I look at it, I don't see what it looks like now. In fact, I have no idea. And I can't know what it looks like now, because the light's been traveling for over 2 years. Yeah?
Does light ever stop traveling?
No. It does not. So, it will dissipate until the amplitude is so small that it's not observable anymore. Right? But no, it doesn't ever stop traveling. So, if you even think about something like the nearest galaxy to ours, called the Andromeda Galaxy, you can see it in the night sky. It's a little fuzzy patch, looks like a fuzzy patch of stars.